fluids book back, numericals and um, conceptuals. The first question where they're talking about blood pressure in the feet is more in a human body than the brain. Obviously, the feet has got a blood column above it. The feet is like this, there's a blood column of the leg above it, whereas the brain does not have any blood column above it. That explains why the feet is experiencing a greater pressure than the brain. The point, sum number B, is they are measuring the atmospheric pressure at a height 6 kilometer from the sea level. They're noticing that there's a drastic change and they observe that it's not linearly proportional to height. Normally, pressure is linearly proportional to height. But whereas in the atmosphere, you have a different layers of air which are of different densities. You know, it's more denser near the surface of earth and less denser above the surface when you go far away, far above the earth. Okay, so then therefore, it is not pressure and height are not linearly varying. The pressure is exponentially varying with height, exponentially decreasing. The pressure as you go above should be lesser and lesser. No, that's why in high up the mountain the pressure is less. Okay, but here it's decreasing exponentially. That is why it is quite different as to the predicted value. If you calculate it for 6 kilometers, it will be different, whereas the actual value is so drastically different. Why? Because the pressure is exponentially varying, so the predicted result will not occur. So let's go to next. Hydrostatic pressure is a scalar, because hydrostatic pressure gets evenly distributed in all directions at any point on the fluid, so it gets cancelled out, it becomes a scalar. That answers the first question. Let's go to second question. The second question, you have a mercury column like this. This is a mercury and the angle of contact, generally in a mercury, the force of cohesion is greater than the force of adhesion and adhesive force is lesser than cohesive force. The angle of contact will be obtuse. Therefore, if you're going to mark this as the angle of contact, you got to mark theta like this. And what is this? This is the force that exerts between the liquid and air interface. This is the force that exerts, or let's say surface tension between liquid and air, surface tension between solid and air. This will be surface tension between solid and liquid, or solid liquid, liquid solid, whatever that is, like mercury and solid. So when you break this down into component, this become TLA cos theta here. Okay, therefore when you break it down as a vector, this plus this TLS plus TLA cos theta will be equal to TSA. Therefore, cos theta is nothing but a TSA minus TSL by TLA. Okay, but you know that for a mercury glass interface, TSA is lesser than TSL. Okay, because TSA is a solid air interface. Surface tension there, and solid liquid, a solid liquid. This will be liquid air. Okay, yeah. So you should know that this is going to be obtuse angle. This is definitely obtuse angle, correct? And therefore this has got to be lesser than this, because cos will be negative only in the second quadrant. Therefore, it's got to be an obtuse angle. That's when you'll get a negative value. The TSA is lesser than TSL. This is a known factor, okay? Solid air, surface tension between solid air is lesser than solid liquid. Therefore, cos theta becomes negative. So this is a very important point. I am saying cos theta is obtuse. As cos theta is obtuse shows that that will be negative. Therefore, I am concluding TSA is less than TSL. For me, the converse is easy. And so then therefore, it always forms an acute angle. We know that reason being the cohesive force is greater than the adhesive force. And this diagram explains why it's obtuse. And then therefore, we can explain everything else. Okay. So then next is a water with detergent dissolved in it should have small angle of contact. Oh no, next is not that. Okay, next question is water on the clean glass vessel tends to spread out while mercury on same surface tends to form drop. Water wets glass while mercury does not wet glass. Very simple. Water wets glass. Okay. Because the force of in the water, what do you know about water and mercury? Mercury cohesive force is greater than adhesive force. Whereas in water, the adhesive force is greater than cohesive force. Therefore, water wets, obviously forming a concave meniscus, whereas mercury will be like this. It's very simple. The water, therefore, what to say? Consequently, mercury does not wet the glass. Can you see? It is not wetting the glass and tends to form a drop. So this is in a beaker. So supposing it's in a glass, the water will spread out here because adhesive force is greater. But when you place a mercury, it becomes a droplet because it has a less tendency to get attached to the glass here, as you can see from here. Can you see? So then therefore it forms a droplet. So that explains it. So next question is, see, the surface tension of the liquid is independent of the area of surface. Surface tension is independent of the area of the surface. Surface tension of liquid is a force acting per unit length. You know, surface tension itself is force per unit length. Correct? And so then therefore it is independent of area. It only depends on the length. The fact that it is force per unit length shows that it's independent of area. That's all, okay? So that completes it. The next question is at E, which is a drop of the liquid under no external force is always spherical in shape. See, when there is no external force, it will have minimum energy. When there's no external force, it tends to be remaining in equilibrium. Any droplet is supposed to be remaining in equilibrium, so it tends to be remaining in a state of minimum energy. Minimum energy also refers to equilibrium. So in the absence of any external force, it should have minimum energy. If it have minimum energy, it should have minimum surface area. Minimum energy indicates minimum surface area. Okay, and so then therefore for a given volume, sphere has minimum surface area. You will learn it in 12th standard. There's a syllabus called maxima minima. For a given volume, the sphere is a shape which has got minimum surface area, and therefore a liquid tends to take a spherical shape in the absence of external force in equilibrium. So let's go to next question. Next question is the third question. The surface tension of the liquid generally, decreases with temperature. Surface tension, okay, decreases with temperature. Increase in temperature decreases the surface tension, okay. So what do you mean? You have you're doing a capillary tube experiment. You have a water which is rising here, forming a meniscus. Due to surface tension only the water is rising, but if we increase the temperature, the height of the water, height level will come down. The height level will come down, or probably it will not even rise, because the molecules tends to move, reducing the surface tension. So then that's what it is. Surface tension decreases with increase in temperature. That's point number A. The B, viscosity of the gas. I told you the coefficient of viscosity is directly proportional to square root of absolute temperature in the case of gases. Why? Because diffusion of the layer happens. When the temperature increases, this diffusion of layer of air from one layer, other layer, it diffuses, which increases the resistance. So it's directly proportional. Whereas in the coefficient of viscosity of gas, whereas in the case of liquid, it will be inversely proportional to temperature. So then coefficient of viscosity decreases with increase in temperature. For a gas, it's increasing with increase in temperature. So let's go to point number C. For solids with elastic modulus of rigidity, the shearing force is proportional to the shearing force. Shearing force is proportional to the shear strain, while for the fluids it's proportional to rate of shear strain. They themselves are given in bracket, you just have to use the right words there. Okay. So this question is for solid elastic modulus of rigidity, shearing force. Um, for solids, you all know it's a shear stress by shear strain. That's what is modulus of rigidity eta, where it's going to become like this, and this will be theta and it's delta L by L, and if you write what is stress therefore is eta into shear strain. Therefore, stress is directly proportional to shear strain. This is in the case of solids, but in the case of fluids, we can never write shear strain because there's no actual, the liquid is going to flow like that. It's not like a solid where you can concretely say it's opposite by adjacent and all that. So it only depends on the rate at which the theta is changing, the angle at which the fall is happening, So the rate of change of that angle, this is called shear strain, rate of shear strain. So for a fluid, it depends on rate of shear strain. For solid, it depends on shear strain. So that completes it. So let's go to next question. For the model of the plane in the wind tunnel, the turbulence occurs at a dash speed. Okay, there's one more question, sorry. For a fluid in a steady flow, the increase in flow speed at the constriction follows from dash, while the decrease of pressure there follows from, I don't understand the question, let me read it properly. Yeah, I understood this. What is it? First point, I think it refers to the theory of continuity. For the fluid in a steady flow, the increase in inflow speed, supposing a fluid is flowing in, the speed increase is attributed to, we know that it's attributed to A, V is always a constant. How did we find this? But considering that a mass is conserved for an ideal fluid, correct? So that we found out using conservation of mass. Okay, the velocity area interrelation was found using conservation of mass, whereas a decrease in pressure, the pressure relation was found using Bernoulli's principles. That fills the second blank. Okay, so let's go to the next question. So this question, for a model of the plane in a wind tunnel, what is this wind tunnel? Normally in NASA and all, they'll have this wind tunnel, a kind of small tunnel, okay, in which they will fix an aircraft and they will blow air into it, high speed wind, so that the aircraft will be stationary, the wind will move. In real life scenario, what is happening? The aircraft is moving, wind is not really stationary, the wind is slightly moving, but there will be high speed wind. The converse situation, where they will test, it will be like when the aircraft is stationary, wind is moving. It's a converse of wind is stationary and aircraft is moving, correct? So that way they test the behavior of the aircraft in a wind tunnel, okay? So then where it has to, they will do a testing for an aircraft, then it has to succumb to a very high pressure, obviously, correct? That is when they can really, than the real life scenario, so that they can test the vehicles, they can test this aircraft. So therefore, the turbulence in general inside a wind tunnel will be greater than what they experience outside, because it's used for testing. So you understood what as the wind tunnel means. So let's go to next. So hope it's recording. One second. Yes, it's recording. Okay, so let's go to next question. To keep a piece of paper horizontal, you should blow over, not under it. When we blow over the piece of paper, the velocity of air increases. As a result, the air gets pushed and the paper starts rising. Okay, so the paper, when you blow here, the air moves and creating a low pressure, and therefore the paper will start rising. So then therefore, for it to remain horizontal, you should blow over, not under it. Okay, one second, hold on, I'm saying the wrong thing, one second. Okay, so I didn't understand the question, now I'm clear. So then supposing you are holding a paper like this, okay? So we blow the paper on the upper side of the paper. When you blow it on the upper side, the velocity increases, so then the pressure here decreases, pressure decreases. Since the pressure under the paper is now greater than the pressure above, the pressure under the paper is greater than the pressure above, the net force, there'll be a force due to downward force and there's an upward force. The upward force will be greater. The net upward force is greater. Correct? Since the net upward force is greater, resulting in the paper being horizontal. So then there is an since there is a net upward force which is going to counter with the atmospheric pressure, the paper will remain horizontal. I hope I made it clear. That was a very difficult question to understand, but now it's easy. So let's go to next question. When we try to close a water tap with a finger, fast jets of water gush through the opening between our fingers. Because the area, when you close it, obviously the area is getting reduced. When the area is getting reduced, the velocity will increase. That's what it happens there. So let's go to the next question. The size of the needle of a syringe controls the flow rate better than the thumb pressure exerted by the doctor. Yeah, when the size of the needle, as you know, when the size of the needle, which is area of cross section, is lesser, you know that the pressure is more. So then the needle of the syringe controls flow rate better than the thumb pressure exerted by the doctor. Yeah, so then because when the area is also lesser, the velocity is more. Okay, when the area is smaller of the syringe, the velocity becomes greater and the pressure becomes lesser. So are they talking about the nozzle being smaller? Let's see. The velocity has more effect compared to the pressure. It is for this reason the needle of the syringe controls flow rate better than the thumb rate. So they're talking about the flow rate of the injection, okay? So the flow rate of the injection depends on the velocity. The flow rate depends on velocity because flow rate is nothing but area into velocity. So then therefore it is easier to control the velocity than controlling the pressure by the thumb. So what is the question? A fluid flowing out of the small hole in the vessel results? No. The size of the needle of the syringe controls the flow rate better. Yes. The size controls the flow rate better. That is the right answer. So let's go to next question. Next this another question. A fluid flowing out of small hole in a vessel results in backward thrust of the vessel. That's because of the conservation of momentum. When there's a forward flow, there's a forward momentum, there'll also be an equal backward momentum which will be on the vessel. That's all. That completes that answer. The spinning cricket ball in air does not follow parabolic path. You expect it to be parabolic, but it's not actually, it becomes unpredictable. It is spinning down, but it's not exactly parabolic. That's because of the Magnus effect. You know the Magnus effect? Due to that, yeah, it's not exactly following a parabolic path because of that. You must remember that, okay? So let's go to next question. The next question is a 50 kg girl wearing a high heel shoes. So mass of the girl is 50 kg. She wears a high heel shoes which has got area diameter to be 1 centimeter. So therefore the area pi r square, which is pi into d square, d by 2 the whole square. R is diameter by 2, pi d square by 4. Pi d square by 4. That will be the area of cross section. And pressure is force by area. Force is mass into gravity, which is 50 into 9.8. By an area of cross section which is pi d square by 4. You know the diameter is 1 centimeter. 1 centimeter is 10 to the power minus 2 meters. So substitute that here. So it's 22 by 7 into 10 to the power minus 2 the whole square by 4. Just do this calculation, you'll get the answer to be 6.24 into 10 to the power 6 Pascal. So that's what it is. That's the next sum. A Torricelli's barometer used mercury, yeah. The Pascal duplicated it using a French wine. So instead of mercury, he's going to use some French wine whose density is 984 kg per meter cube. The density of mercury is 13.3 kg per meter cube. 0.6 kg per meter cube, yeah. So whereas here it's 984 kg per meter cube, which is quite high, correct? Density is so high, so the height will be correspondingly less. To find the h, you can use, pressure is equal to h rho g. The pressure will never change. It will be 1.0, atmospheric pressure 1.013 into 10 to the power 5 is equal to h, we don't know. Density we know is 984 into g is 9.8. With this you can calculate what is your height. It will come to be 10.5 meter. 10.5 meter. Normally with the mercury density we get 76 centimeter to be the height. This is much higher because the density is 13.6 10 to the power 3 here. Sorry, 10 to the power 3. It's such a density is much larger. When the density is much larger, the height will be lesser. But here the density is low, so the height will be more, and that's what it is. Okay, so let's go to next. A vertical offshore structure is built to withstand a maximum stress of 10 to the power 9 Pascal. It can withstand so much stress, okay? A vertical offshore structure is built to withstand a maximum stress of 10 to the power 9 Pascal. Is a structure suitable for putting up on the top of an oil well in ocean? Take the depth of the ocean to be 3 km. The depth of the ocean is 3 km, then the height will be 3 into 10 to the power 3 meters. And density of water is 10 to the power 3 kg per meter cube. The sea water, of course, the density is slightly higher, but we can take it for now. They have not given it, so we can treat it as normal water. So the pressure due to sea water will be h rho g, which will be 3 into 10 to the power 3 into density is 10 to the power 3 into gravity is 9.8 Pascal, which is 2.94 into 10 to the power 7 Pascal. Since the pressure of seawater is less than the maximum, so basically you're digging an oil well in the ocean, okay? This is the ocean. You're digging an oil well in the ocean. And on the top of it, you're putting up this building offshore, that structure, which can withstand 10 to the power 9 Pascal. So then there will be height of the seawater above it, which is depth of seawater, which is going to exert a force of 2.94 10 to the power 7. This is definitely less than 10 to the power 9 Pascal that the building can withstand. So then therefore you can put it, no problem. It's fine. Okay, so I hope you understand what is this oil well, where is it? It's under the sea, and so then you're putting up above the oil well, you're putting up a building there, a structure there. So then you understood what it is. Okay, so let's go to next, because people do work in oil well, and so then they'll have to have a building there, an accessory structure there to do these operations, and so that building has to be constructed with so much that it can withstand the pressure of the sea. So that it completes it. Let's go to next question. Is the 8th question. A hydraulic automobile lift is designed to lift cars with a maximum mass of 3000 kg. It can lift, automobile lift, okay? I'm imagining a crane. It's an automobile lift which can carry 3000 kg. The cross-section area of the piston carrying the load, area of the piston carrying 425 centimeter square, which is 425 into 10 to the power minus 4 meters square. The maximum pressure would the small piston bear? Pressure is always force by area. Force is m into g. That's going to carry 3000 into 9.8. That is the force. By area is 425 into 10 to the power minus 4, which will be 6.92 into 10 to the power 5 Pascal. That explains that. Let's go to next question. 9th question. A tube contains water and spirit separated by mercury. Okay, the mercury column in 2 arms or the level with 10 centimeter of water in one arm and 12.75 centimeter of spirit in the other. What is the relative density of the spirit? So this is the diagram. You have a mercury column in here which is at the same level, okay, which consists of a 10 centimeter of water column above it and a 12.75 centimeter of a spirit column on the right side, okay, the left and right side. Since the mercury is occupying the same level, the pressure exerted by this and the pressure exerted by this, that's water and the spirit are same. You know that's H rho g. This H rho g has to be equal to this H rho g. So let's consider H dash, rho dash and g. The g and g anyway get cancelled, so H is nothing but 10 centimeter. You don't have to, because the ratio you don't have to convert into meters, into density of water is 10 to the power 3, which will be equal to, okay, centimeter, no, okay, this is in, we are keeping it in centimeter, otherwise convert height also into meters. Density of water in CGS unit is just 1 gram per cc. So you just retain it as 1 is equal to H dash, which will be 12.5 into rho dash. With this you can find what is rho dash. Rho dash therefore is 10 by 12.5. 10 by 12.5, which should be equal to 0.8 gram per centimeter cube. That's a specific gravity, which is relative density. Specific gravity, no, that's the, 0.8 grams is actually the density, not the relative density. You get the density, actual density of the spirit. Once you get the actual density of the spirit, they are asking relative density. Relative density is the density of the substance by density of water at 4 degrees Celsius. So which is nothing but relative density is 0.8 by density of water at 4 degrees Celsius is 1 gram. So then therefore 0.8. It has no unit. Relative density is density by density, and so it has no unit. Okay, so that completes this question. If 15 centimeter water and spirit each are poured or further poured into the respective arms of the tube, what is the difference in the level of mercury in the two arms? So the same question we are adding, okay, which means to the left side it's 10 plus 15, it becomes 25 centimeter of water column. The right side we have spirit, which is 12.5 plus 15, which is 27.5 centimeter of spirit column. And you know density of water is 1 gram per centimeter cube. Density of spirit, you just found it to be 0.8 gram per centimeter cube. And the density of mercury in CGS unit is 13.6 gram per centimeter cube. Its SI means 13.6 in 10 to the power 3 kg per meter cube. Okay. So then all this we have noted down. What are they asking? What is the difference in the level of the mercury? Will there be an difference in pressure now? Because their height has changed. The pressure exerted by the H1, say the water column on the mercury column is just H rho g. Okay, 1 second, hold on. The difference in pressure between the water and the spirit. Supposing, let's assume the water is exerting a pressure of rho 1 H1 g. The spirit is exerting a pressure of rho 2 H2 g. The difference in pressure will be so much, right? So g can be taken out common, rho 1 H1 minus rho 2 H2. So it's the height is 25, is the density you know is 1, minus the height is 27.5, you know density is 0.8, hence the answer is 3g. And so that will give you the difference in pressure between the water and the spirit, correct? Yeah, but what is the question now? The difference between the level of the mercury in the two arms. Oh, they're asking about, so yeah, there is a difference in pressure, which is 3g, which will attribute to a height difference in the mercury column, which will be equal to H rho g. H rho g is equal to 3g, g and g get cancelled. So H rho is equal to 3, where this H rho g stands for the difference in the level of the mercury column in the U-tube manometer. So the density of the mercury is what you have to take. So you know the H is what you have to find, 3 by density of the mercury, which is 3 by the density of mercury is 13.6. So the answer will be 0.221 centimeter approximately, okay. So that will be the difference in the height of the mercury column in the two arms. That's the question, okay. So next is, let's go to 11th question. Can a Bernoulli's equation be used to describe the flow of water through a rapid motion in a river? No, you cannot apply it for a river and all. Bernoulli's equation is only for an ideal fluid, so therefore you cannot consider it for river. Does it matter if one, next question, does it matter if one uses gauge instead of absolute pressure in applying Bernoulli's equation? Gauge pressure, this is gauge pressure, this is absolute pressure, which is this plus this. Is it okay to just use gauge pressure while applying Bernoulli's? You can use gauge pressure provided the atmospheric pressure and both these points are the same, because if you put Bernoulli's, you have what to say, see, suppose you take a liquid, okay, this is a gauge pressure H rho g, this is the absolute pressure which is H rho g plus Pa. So you know the pressure here is quite different to the atmospheric pressure. In that case, you cannot use, if you're going to apply Bernoulli's at every depth, you cannot take just the gauge pressure and do it. You have to consider it. But if in case at these, supposing you're going to consider a layer of air, okay, and you're going to look at the pressure difference. Okay, 1 second, hold on. See, let me explain this part clearly. It's not clear. Okay, so let's take this Torricelli's reflex experiment, which will help you to understand this better. Okay, you have a pressure here, which is P. Here I have a atmospheric pressure. In that case, I am allowed to take a H rho g, which is the pressure difference between that and this, which is just a gauge pressure. So yes, it does not matter if one uses gauge pressure instead of absolute pressure. I don't have to necessarily take an absolute pressure at this point. I'm just taking the gauge pressure when I'm calculating. So then it's okay to take a gauge pressure instead of, provided the pressure at the two different points are different, it's not the same. Okay, it's significantly different pressures, then I can do it. I hope I've explained it well. I don't know. Okay, sorry guys, that's as much as I could explain. I've done it. So we can discuss in the class if you want. Next is, a glycerin flows steadily through a horizontal tube of length 1.5 meter of radius 1 centimeter. If the amount of glycerin collected per second is 4 into 10 to the power minus 3 kg per second, which is the rate of flow of fluid, which is Q, which is also equal to AB. Okay. While the pressure difference between the two ends, what is the pressure difference between the two ends of the tube? Okay, for which there is, you won't know this because this derivation we have not done. It's called Poiseuille's formula. The Poiseuille's formula we didn't deal with. It was dimensionally derived. Okay, I'll tell you the formula. The rate of flow of fluid itself is proportional to pressure difference between this end and that end, because liquid flows because from high pressure to low pressure there will be a pressure difference between this end and this end. So it's P by L, pressure by length, which is called pressure gradient, due to which the flow is happening. R to the power 4, the radius to the power 4, and a coefficient of viscosity here, and a pi by 8 is a constant. This is the formula for rate of flow of fluid according to Poiseuille's formula. If you know this formula, then you know the volume of the fluid. Rate of fluid has been given to be 4 in 10 to the power minus 3, and the pressure per unit length, have they given the pressure difference between the ends? The question is about finding what is the pressure difference. Yeah, so P by pressure difference between the two ends. If you know the length of the tube, you can substitute there, radius, everything is given, so you can find P. Very, very simple. So for which you should know this formula, without which you can't do it. And you should have eta. If they had given eta, can you see viscosity of the glycerin has been given to be 0.83 Pascal second. So they have given the coefficient of viscosity there. So that gives you the pressure, which will be equal to 9.75 in 10 to the power 2. But we have, schools are not dealing with Poiseuille's formula, so I also ignored it. But if you can memorize this, according to Poiseuille, it's pressure by unit length, the radius to the power 4, and inversely proportional to coefficient of viscosity, and a pi by 8. That helps you directly to find this answer. So let's go to next. In an experiment on the model aeroplane in the tunnel wind, in a wind tunnel, the flow speed on the upper and the lower surface. So supposing an aircraft is fixed here, okay, and the wind, you know what happens in the tunnel. I've told you the wind flows at a greater speed and they're testing it basically. So at the upper end it's 70 meter per second. So I hope I recorded this. I'm not sure if the area is greater, the velocity is lesser, so pressure is greater, so the height should be more. It shows that this is wrong and this is correct. Let's go to the next question. A cylindrical tube of a square pump. A cylindrical tube, but it's got a square pump. Okay, a pump attached to it. I don't know. A tube in which a pump is attached to it. The pump is squarish. It's got pores. It's got small holes. If the liquid flow inside the tube is 1.5 meter per minute, what is the speed of ejection of liquid through the holes? The total cross section area, there are 40 holes, okay. So there are 40 holes and each of small holes which are circular in shape, which is so then 22 by 7 pi into r square. You have given the diameter of every hole is 1 millimeter. So the radius therefore is 1 by 2 millimeter, which is 1 by 2 into 10 to the power minus 3 meters. So it's 1 by, when you square it, it's 1 by 4 r square. Into 10 to the power minus 3 the whole square. So that is the pi r square. You'll get answer to be like this. This will be the total cross section area available for the water to come out. Okay, now you know the speed inside the tube is 1.5 meter per minute. So per second it will be 1.5 by 60. That will be the meter per second. That will be the speed, velocity inside the tube. So you know that you know A1 V1 is equal to A2 V2 according to theory of continuity. So supposing you want to find the velocity of the outflow, V2 is equal to A1 V1 by A2. So A1 itself is area of cross section. They have given area of cross section of this tube, which is 8 into 10 to the power minus 4 into the velocity of that is 1.5 by 60 by A2, which is the pores, small pores area, which is 22 by 7 into 10 to the power minus 5. You will get V2. So that is basically, there is a cylindrical tube through which a pipe is attached, which is squarish, in which there are poles through which water is coming out. So I am doing theory of continuity for this and this. A1 V1 is equal to A2 V2. I hope you understood. Okay, so let's go to the next question. U-shaped wire. A U-shaped wire is dipped in a soap solution and removed. The thin soap film formed between the wires and the light slider supports a way of, okay, well, let me read the question and then explain to you once again. So we are inserting a U-shaped wire and a soap film is formed in the wire, okay. So that's the question. The length of the sliding wire is 30 centimeter, okay, and the weight including the soap film formed and the slider is 1.5 into 10 to the power minus 2 newtons. So then you know that the weight is nothing but mg, which is also equal to the force, downward force, which is also equal to the surface tension. That's also force. Surface tension is equal to force per unit length. So then therefore force is equal to surface tension into length. Can we write tension into length? Tension into length. But here it is U shaped, so then the length becomes 2L. It is not L, it is actually L and L, it becomes a 2L length. So therefore, since the length of the slider is given to be 30 into 10 to the power minus 2, you double it and write it, and so then you can get surface tension to be mg by 2L, and you just plug in the values by 2 into L, which is 30 into 10 to the power minus 2, you get 2.5 into 10 to the power minus 2 Newton per meter. So that completes the sum. Let's go to 18th question. Eighteenth, 19th, 20th, 21st, 22nd, 23rd, 24th. Oh my god, such a huge lesson. I'm not going to finish it now, I think. So I hope this helps, whatever I've done. The rest of it will try to go through, and if you have doubts, you ask me, okay?